Welcome to the video on the foundations and architectures of computer networking. We'll explore the principles, protocols, and technologies that power modern digital communication. In this executive summary, we see that computer networking involves interconnected devices using protocols to enable global sharing, cloud services, and digital security. Core technology includes nodes, media, protocols, and data systems. Real-world applications span banking, IoT, smart cities, and AI integration. Future trends point towards 5G, 6G, edge, SDN, and quantum networking. Computer networking is the foundation of today's digital ecosystem. Computer networking is vital for global communication, business and commerce like e-commerce and digital payments, and enabling cloud computing. It is essential for the Internet of Things, artificial intelligence distributed systems, and critical for cybersecurity functions like encryption and secure monitoring. Every modern digital technology relies on networking as its underlying foundation. A computer network is a collection of interconnected devices that exchange data using standardized protocols. The process involves a device generating data, converting it to signals, traveling through a medium, forwarding, and finally being received and processed by the destination. The major components of a network include end devices or hosts, servers, and networking devices like routers and switches. Communication rules are defined by protocols like TCP/IP and HTTP, which travel across transmission media such as fiber and wireless channels. These components must work together seamlessly for effective network function. The historical evolution of computer networking began with the telegraph era and the telephone. Key milestones include ARPANET, the introduction of TCP/IP, Ethernet, and the World Wide Web. More recently, we have seen the rise of cloud computing and the current advancements in 5G and AI. Modern networking evolved through decades of innovation into a globally interconnected digital ecosystem. The key objectives and benefits include fast data communication and resource sharing. Reliability and fault tolerance are provided through backup systems. Networking enables centralized management, global collaboration for remote work, and distributed computing for AI and big data. Networking transforms individual devices into powerful collaborative systems. The 5 fundamental components of data communication are the sender, the message, the transmission medium, the receiver, and the protocol. These components are essential, as a communication system fails if anyone is missing or malfunctioning. Protocols are the rules that govern the exchange of information. Transmission media is classified as guided or wired media, such as twisted pair, coaxial, and optical fiber, providing high speed and security. Unguided or wireless media, like Wi-Fi, cellular, and satellite, offer mobility but with variable speed and lower security. In practice, modern deployments combine these approaches. Wired networks use physical cables for high speed and low latency, but they are costly and limit mobility. Wireless networks use electromagnetic waves for mobility and easy installation, but face interference and variable speeds. Organizations typically use a hybrid approach to combine the advantages of both. Networks are classified by geographical coverage into PAN, LAN, MAN, and WAN. PANs cover a few meters, like Bluetooth earbuds. LANs cover a building or office with high speed. MANs cover a city or metro area. WANs, such as the Internet, span worldwide coverage, connecting MANs and LANs. Network topologies define the arrangement of devices. Common types include star, bus, ring, mesh, and tree. The star topology dominates modern networks due to its centralized management, high reliability, and scalability using network switches. Topology choice impacts performance and maintenance. Essential network devices include hubs, switches, routers, access points, and firewalls. They are responsible for connecting, managing, routing, and securing data traffic. For example, a router connects different networks, while a firewall filters traffic for enhanced security. Protocols are the universal language of networking. Examples include HTTP, HTTPS for web access, TCP for reliable delivery, and IP for addressing. These standards, governed by organizations like IEEE and IETF, ensure that billions of devices can communicate seamlessly worldwide. Packet switching is the foundation of modern networking, enabling efficient data transfer. It works by creating data, packetizing it, routing packets independently, transmitting them, and finally reassembling the message at the receiver. This method offers efficient bandwidth, fault tolerance, and scalability. The OSI model is a 7-layer conceptual framework for standardizing network communication. Its importance lies in simplifying networking, standardizing communication, enabling easier troubleshooting, and supporting interoperability. A handy trick to remember the layers is, all people seem to need data processing. The TCP/IP model is the practical 4-layer networking model used by the Internet. It is highly scalable, vendor-independent, and provides reliable communication. The process flows from the user request through the application, transport, internet, and network access layers. Comparing the two models, OSI is a 7-layer theoretical framework excellent for learning and troubleshooting. The TCP/IP model is the 4-layer practical internet standard widely implemented for real-world compatibility. OSI helps us understand networking, while TCP/IP powers the internet. The internet is a global network of networks using TCP/IP, connecting clients, servers, routers, and data centers. DNS, the internet's phone book, translates domain names into IP addresses, making the internet easy to use. The DNS resolution process is critical for accessing websites securely. Cybersecurity is essential for protecting networks. The core pillars are confidentiality, integrity, and availability, known as the CIA triad. Key security mechanisms include firewalls, encryption, authentication, and IDS/IPS to protect against attacks like MITM, DDoS, phishing, and sniffing. Network performance is measured by core metrics like bandwidth, throughput, latency, jitter, and packet loss. These metrics are vital for network design, troubleshooting, and ensuring quality of service. Different applications prioritize different metrics, such as low latency for gaming and high throughput for streaming. Emerging technologies are shaping the future of networking. These include software-defined networking and network function virtualization for flexible control, cloud and edge computing for localized processing, 6G networks for ultra-fast speeds, and quantum networking for absolute security. These innovations create a dynamic and intelligent networking ecosystem. To summarize, we covered network types, topologies, protocols, the OSI and TCP/IP models, and cybersecurity essentials. Understanding these fundamentals is the first step toward advanced careers in networking, cloud services, and security. Thank you for watching this video on the foundations of computer networks. We hope this knowledge provides a strong base for your understanding of the digital world.